Okay, so this section we're going to start talking about chemistry. And so we're going to start off with talking about atoms. It's going to be a little bit of review from when we talked about electricity. And then we're going to do a little exploration of the periodic table because you're going to be using it quite a bit in this set of chapters. So let's just start off with first taking a look at atoms. So atoms, most of the atoms in the universe are actually hydrogen. So 90% of the atoms in the universe are hydrogen atoms. Everything else are the other things that we'll see on the periodic table, but they only make up 10%. The other atoms are created from hydrogen, and they're going to be created in stars and supernovas. So if you've heard the phrase, you're made of star stuff, that's where it comes from, because those atoms, the hydrogen atoms, get smashed together with the heat and pressure in the sun or stars and get created into these bigger elements. They're small, so each time you breathe out about 10 billion trillion atoms. And that also means that every time you breathe in about 10 billion trillion atoms. So incredibly tiny. And they're so small that we can't see them with visible light. So the way that we see things with visible light is, like we talked about in the previous chapter, light interacts with things. And it interacts by bouncing off of objects. Well, individual atoms are so small, as you can see over in this diagram here, that wavelengths of light miss them. And so we can't actually see them with regular light. So that's why with a microscope, you can't see individual atoms. You can only see groups of them when they make up, for example, organisms. So we have to use what we call scanning probe microscopes. And I have a picture actually on the next slide to show you how these work. That's actually how this picture up here was taken, was with a scanning probe microscope, so we can see the individual, in this case, carbon atoms in these carbon rings. So incredibly tiny. And then as we kind of talked about previously, they're empty. So a atom the size of a medium-sized airport, like Columbus Airport, would have the nucleus the size of a basketball sitting in the middle of it, and the rest of the area would be empty with the electrons kind of spaced throughout the rest of the airport. So let's take a look at how one of these scanning probe microscopes work, because it's kind of neat. At least I think it's really neat. So they work along the same lines as an old record player. So it's hooked up to a computer, and that computer is hooked up to a laser detector. So we've got a laser that is pointing down to the instrument, and then that laser is going to bounce off of it and onto a mirror and then into the detector. So what is the laser basically working off of? It's working off of this lever right here. And when I say it works like an old record player, I literally mean it works like an old record player. So if you look, it's got a needle on it, and it's got a really, really tiny needle. It's got this very tiny probe tip. It's microscopic. That's on the end of the lever. So here's the probe tip out here. And that cantilever is going out and it's running across the surface of the sample. And so it bounces up and down. Every time it hits an atom, it goes up, and then when it gets in between the atoms, it goes down. And so as it goes up and down, the laser light bounces up and down, and so that's what's being measured by the detector and then translated by the computer. So this allows us to not only visualize these atoms, but it's actually allowed some researchers to start moving atoms around individually. And so if you go out and search online, you'll actually find where researchers have written things or drawn pictures in atoms. So they've been able to create pictures and so forth at the atomic scale. It's really kind of cool. So atoms, this is just kind of an overview because again, we talked about this back in the electricity. So if you want to go back and see that as another review, you can. But remember, atoms are the smallest unit that can't be subdivided without losing its properties. So you need an atom in order to have the properties of that material. The subatomic particles, the pieces that make it up, are our protons with that positive charge and the neutrons that are neutral. These guys hang out here in the nucleus. And then we have the electrons, and those guys are negative. They hang out in their electron cloud outside of the nucleus. And then remember that normally an atom will be electrically neutral, meaning that the electrons and the protons are going to balance out unless something happens for that atom to gain or lose electrons. All right, so elements, because we're going to be using some different terms, so you'll pick up some terms as we go along. So an element is a material that's made up of only one type of atom. So all of the atoms in that material are the same exact atom. And so we've got, for example, down here, gold, so all gold atoms, nitrogen. So nitrogen gas is made up of just pairs of nitrogen atoms. And then carbon. So it's showing you in pencils. So graphite in pencils is made out of carbon. But also something like coal or diamonds is actually going to be made out of just carbon for the most part as well. So where would you find these elements listed? Yeah, the periodic table. So if you wanted to find any element, you're going to look for it here. Now this is a very, very simplified periodic table. This periodic table has very little information on it. Most periodic tables have more, and I will actually post on Go Studio with next to this lesson a periodic table that has more detail on it that you can use. You can print it off or you can just save it to your computer. That way you can use it to look up the information on the different materials. So let's talk a little bit more about atoms and what kind of information we can actually find about them on the periodic table. So the periodic table is going to tell you information like the atomic number. So here you can see this periodic table zoomed in has a little more information. So the atomic number is going to be the whole number that usually sits above the symbol for the element. Or down here you can see that this has two numbers. If it's written this way, the atomic number is going to be the bottom number. It will also generally be the smaller number that's listed if you see it written this way. So what is the atomic number going to tell you? The atomic number is going to tell you the number of protons in the nucleus. So that's the one thing that it's guaranteed to tell you about that atom. It will tell you the number of protons in the nucleus because the number of protons is what gives that atom its properties, its physical and chemical properties. If you change the number of protons, you change the element. So for example, with helium here, helium has 2 protons because it has an atomic number of 2. If we remove a proton from it, so it just has 1, then it becomes this guy down here because this guy has an atomic number of 1 and it becomes hydrogen. So very different materials. So they're both gases, but they have different chemical properties. And you may be familiar with helium because that's the one that we use to blow up balloons, makes your voice sound funny. It's inert, meaning it's non-reactive, versus hydrogen, which you can also use to blow up balloons, but we generally don't do that because this one's explosive. So you can see that 1 proton can make a big difference. Each element does have a unique atomic number because those number of protons dictate how they're going to interact with the environment. There are currently 118 elements that have been identified. That number may change as we identify and certify more elements. Out of that 118, 19 of them occur, or I'm sorry, not 19, 90 of them occur naturally on the planet. The rest of those elements are man-made elements. So you can find 90 of them naturally. Some of them are more abundant than others. So some of those natural elements are rare. But the other elements out of that 118 are man-made and generally not in huge amounts. Now, in neutral atoms, the atomic number will tell you not just the number of protons, but the number of electrons, because those two have to equal each other. However, if the atom is not electrically neutral, it's gained or lost electrons, then the atomic number will only tell you the number of protons. There's one other thing to know about atoms related to information that you're going to find here on the periodic table, and that's what we call isotopes. Isotopes are atoms that have the same number of protons, but they have different numbers of neutrons. So if we take a look here, we've got 3 different atoms of hydrogen. So you can see it along the top, they all have 1 proton, so equal numbers of protons, but they have different numbers of neutrons, and that changes their mass. So this hydrogen has just 1 unit of mass, this one has 2, and this one has 3, and you can see they actually have different names. So the isotope of hydrogen 2 is called deuterium, and the isotope of hydrogen 3 is called tritium. And this doesn't really change much about their properties, it just changes the mass. And this actually affects the things about like how we might be able to use them, because it does change their properties a little bit, but not massively. So let's take a look at as far as atomic number. So I've put a few things in here just for you to practice and take a look at. So using the periodic table that I've posted, take a look and see if you can figure out how many protons are in carbon. So I've put these in with their atomic symbols, the letters that represent them. How about in nickel? And in lead. So before I go to the next section, I'm going to actually back up and show you another item that's on this periodic table. It's listed here to show you what it is. The bigger number, or if you're looking at it here, the top number is the atomic mass. And the atomic mass is how you figure out how big the atom is, but you can also use the atomic mass to figure out what the isotope is. So let me grab my pen. So for example, helium right here has an atomic number of 4.03, but we're 003, but we're going to round. So if it's got an atomic mass of 4 and it's got 2 protons, and the mass number of a proton is 1, then we know that it's got 2 masses left, 4 minus 2, and that's going to tell us that it has 2 neutrons in it. And so we can do the same thing with hydrogen. If we know we have hydrogen 3 or H3, if we're told that, that tells us that this is an isotope, that it's a different version of hydrogen. And so we would look up and see that the atomic number for hydrogen is 1. And so we would know that H3 is the mass, if it's given to us with that number. And so 3 minus the 1 tells us that there are those 2 neutrons in that version of hydrogen, which we can see here. Okay? So if we take a look at what I've got here on the slide, so then the other thing I've got here for you to practice on the periodic table is how many neutrons are in these guys. So when you look up the atomic mass on these, you'll see that this, for uranium 235, is not the normal atomic mass. I think that the normal atomic mass for uranium is 238. So this is an isotope. It's a different version. So you're going to find the atomic number for uranium, subtract it from 235, and that will tell you how many neutrons there are. Vanadium, you take that one, look it up, and then aluminum. And I will post in a separate video how to find these. One last thing to talk about in this video on atomic mass, and that is how we get those mass numbers. So if you look at the periodic table, you'll notice that the mass numbers are almost all decimals, like this one. And we just saw that the mass number is equal to the number of protons plus the number of neutrons. But why are they decimals, right? If they're number of protons plus the number of neutrons, it would make sense that it would be a whole number. So the thing is that those atomic weights on the periodic table are determined by the average of the isotopes based on their mass and their abundance in nature. So some of the isotopes are more common than others. And so that's how they get the average, basically, atomic weight. And so if we look down here at the example, we've got nitrogen 14, all right, N14, and we've got, I meant to just point, we've got N15. So this guy has got the atomic number of 7, 14. So this guy has 7 neutrons. Down here, we've got N15. So it's got 8 neutrons. So we know they're different isotopes. N14 is incredibly common, 99.63%. Almost all of it is going to be N14, but we have a little bit of it that's N15. And so and I'm not going to ask you to do these calculations, but just so you can see how it works. So they're going to take the amounts, so you can see N15 has that higher atomic weight, multiply it by its percentage in abundance, same for N14, and that will give you, when you add them together, the atomic weight, which is this 14.067 or 0067. So you can see it's just a little bit more than the normal N14 isotope. So that's why those are mostly decimal points, because of that average abundance. All right, that's the end of the introduction to atoms and atomic mass. Pick up in the next video talking about electrons and how they are interacting with atoms.